Thanks everyone for joining this webinar. We're continuing to try to put out more content and webinars for our customer base, both from a commercial standpoint and certainly a technical standpoint. This is specifically what we call a Powerside technical webinar, and this topic is going to be discussed by Chris Duffey. He's our senior technical fellow with Powerside. He's been with us, started with us last year, and the topic here at hand is utilizing reactive power compensation for mitigating voltage sags due to motor starting. It's a very big topic, but one of the things at Powerside that we are very good at is offering very detailed engineering services that allow us to correct for power quality issues that arise from various phenomena. So today we're going to be talking about motor starting, both with variable speed drives, soft starters, etc. And Chris, extensive background in electrical engineering. He spent most of his career dealing with either software or software modeling, as well as considered an industry expert in the power quality realm. So we're very grateful to have him here with Powerside. And with that, Chris, I'll hand it over to you to deliver the message.
All right. Well, good morning, everyone. Hey, quick confirmation that you can see the first slide. Is that showing up, everyone? Just a
yes,
quick.
Chris. Yep.
Okay, looking good. All right.
Yeah.
So, well, it's either good morning or good afternoon for you, or actually during this presentation, you'll be transitioning from morning to afternoon. But we're going to talk about motor starting, and we're going to build some background so that when we get to utilizing reactive power compensation, that we kind of understand the reasons why for this webinar in particular, we're going to be discussing PSCAD simulations, which offers full transient detail of everything that's going on in the motor start, and especially the things that you want to see that normally you wouldn't see with other motor starting packages. So with that, let me move ahead. Our main agenda, we'll have a quick overview of motor starting and some of the performance data that comes with it. We're going to look at simulation methods. Then next, we're going to specifically look at the PSCAD motor modeling. We're going to discuss sag mitigation because there's several forms of sag mitigation that people employ when they're addressing motor starting conditions. And then finally, the last part will be the key section here where we're going to be talking about applying switch VAR compensation in PSCAD and looking at the simulation results and the key benefits that we can obtain there. So motor starting voltage sag issues. Yeah, when they appear, they're typically caused or impacted by one or more of the following. Motor, the high current draw from the motor itself, the poor power factor of the motor, typically ranging somewhere between 0.1 to 0.25, the starting time, the upstream impedance or high impedance, which is typically where you get the greatest amount of voltage sag depth, the lack of sag mitigation equipment, or the inability of that equipment, like a reduced voltage starter or a soft starter, to basically lower the starting current enough or to compensate enough. And low voltage impacts to the implant equipment, that would be a reason why we'd want to address it, because something might be tripping offline. Also, of note in this presentation, which we'll discuss when we get to the compensation part, of tight utility voltage drop and flicker criteria in the range of 2 to 3%, which can be seen and can be required by the utility or the supplier. The utility unable to strengthen its grid economically, it costs a lot of money to strengthen the grid. And so that's kind of an undesirable way to go unless you want to move your whole plant. Too large a motor for a given system short circuit strength. And I think that's also going to play out today at the end when we talk about VAR compensation. Complaints from customers on the same feeder, and you could go on. We could just keep going on to this list. But basically, those are the kind of things that are going to lead us into addressing an issue that we have. Now, for starting points, it's very clear. We can get the NEMA code off of the motor, and from that code, we can extract what what the motor starting conditions will be in terms of the starting current. But the one thing that we're missing from this is the starting power factor, and that's kind of unfortunate that the NEMA code doesn't include a nameplate code for like starting power factor. So kVA per horsepower is great, but it's only half of the motor impact equation. So if we combine this also with the fact that often motor starting power factor is not included. I've probably done, I don't know, hundreds of motor start simulations, and in the data that I've received to perform those, I don't know, maybe 30% of them had the actual starting power factor of the motor. But if you don't have it, and it is a pivotal piece of information, I would suggest choosing a low value like 0.1. So it's mostly VARs that are going to be drawn by the motor, which causes the greatest voltage drop for a reactive system. Here's some other typical data that we'd see for motors. This motor performance curves include the current versus speed and the torque versus speed for two different voltage conditions. And here we see 645% for the locked rotor current. We can see that over here. And for the locked rotor torque, it's about 90% or so. And how about some other effects showing how they actually behave on a system? For instance, if you had a 10 MVA power draw and you change the power factor on this system. So here we have a 5 MVA transformer. It's X over R. It's 10 in this case. And I've plotted two cases where the X over R is 10 and 2. You can see that it makes sense, right? That as the power factor gets worse, the voltage drop is going to get worse. And if the upstream X over R ratio is lower, you're going to see that voltage dip occur earlier. So there's some interesting system behaviors that are happening, and that's why it's important to have a good upstream system model when you're doing your motor starting simulations. How about a distribution feeder? So in this case, you can see along this very simplistic, feeder, you can see that it's pretty obvious as the further you go down the line, you're going to find the short circuit amps are going to be decreasing. You're going to find the X over R ratio itself is also going down. And of course, the voltage drops the further you go down the feeder. So if you're in a weak area near the end of the line and you have a large motor you have to start, obviously that's when a lot of compensation is needed in various forms. So I like this chart. I think it basically shows us that further away, weaker, but there's a couple things going on. It's not just impedance. It's also X over R ratio. You're at the substation where you have a high X over R from the transformer. You get near the end of the line with the X over R of the conductor maybe being 1, maybe being 2. The further you get down the line, the lower the X over R gets. So all of these are going to impact our evaluations in terms of how much voltage dip or how much voltage sag we're going to get. Now, there's various simulation methods, but the key factors that I've seen over the years are that many engineers are not really aware of what's on the inside. And we're hopefully going to talk about that today. We're going to show you what's on the inside, all right, as best as we're able to. And so if you're not aware of what the tool is doing on the inside, you may not really understand the full scope of the application, what you can really get out of it and what you can't. Often typical data is used instead of the actual motor performance data. Why? Because it's convenient. It's been provided. So you'll automatically jump into that category when you need to get your work done quickly and you haven't really struggled to get that motor performance data. And boy, I'm with you in terms of the struggle to get good data. Trust me, I understand what lots of bad data looks like. And so it is often a struggle to get that information. Some other key factors. To gain confidence in a tool's result, boy, I really recommend benchmarks, hand calculations, spreadsheet calcs. They're essential to make sure you have confidence in the tool that you're using. Getting accurate motor performance curves, again, I'm going to say it again, can be very difficult, and I do understand that, and I understand the bad data that's being thrown around on a lot of motors. A few more. things that will really impact our simulations: motor, shaft, and load inertia. If starting time is critical to you, well, you better have that information, because that determines, besides the motor torque on the shaft itself, the key factor that's going to lengthen or shorten start time is the inertia. And if you want to have a good idea of what that is, how long the start time is, you need that inertia. The motor loading curves are essential also, especially if you're going to simulate stall effects. Performance curves for double cage parameter derivations and flux models are necessary when you're going to do those. And in those simulations, you're going to simulate full dynamic response. You want accurate voltage feedback impact and power swings to be seen and stall conditions to be seen. You're going to up your simulation detail. And so you're going to need more information. You're going to need the performance curves. You're going to have to do some derivations to get parameters. The last key factor here is that performance curves, interestingly, just note this, they're not dynamic curves. These are static curves. In other words, it's like you put a motor under test. You put it on a dynamometer, you take it to a certain speed, you record the conditions of the motor. You go to another speed, you record the conditions of the motor. So, and they let it settle. So these are not curves that are going to give you any idea of time constant effects or any type of delays that are built into the rotor model, which it responds over time. And in fact, if you were to look at a flux model for a motor, the major time constant, T prime D0, is often 2, 3, 4, 5 seconds. Imagine that. The inside of the rotor, it's taking 2 to 5 seconds to respond. And so that's important if you want to see voltage impact effects. And if you have a really fast starting motor, you're going to get less torque out of the motor. All right. So do you know what your motor starting tool is doing? Consider the following simulation methods. And we're going to be looking at these from top to bottom, least complex to most. A power flow simulation or load impact, and I'm sure many of you know those and use them. I'm going to call these two hybrid 1, hybrid 2. The first one takes performance curves and performs that and does lookup on the curves, uses inertial dynamics and then a network model. Hybrid 2 changes the performance curves to equations, but includes dynamics and network. So we're going from a single time to a time simulation, and then a full flux model and dynamic simulation is a time simulation. And then more detail, we go to a full 3-phase transient simulation that has the full transient model of the network and everything, and inertial dynamics, and finally finite elements. So let's look at each one. So for power flow, it's an RMS motor starting calculation. It typically uses a Thevenin or Norton source model technique and the motor starting impedance, which is a constant impedance. So you're going to measure, if you figure out what that is, or take that from your data and then employ it onto the network model and see the voltage reduction. Some key characteristics. It simulates that single moment when the motor's first switched on. It's not a time simulation. And the motor, again, is simulated as constant impedance. The simulator must include an iterative Y-bus simulation. If any other type of non-constant impedance loads are used, it needs to be able to iterate. But note that a Newton-Raphson technique is not adequate because how low the voltages typically go. So it has to be an iterative Y-bus. It's similar to a short circuit simulation, and the swing source has to have its impedance included in the model so that you get the voltage drop from the swing or from the source impedance. The simulator should include a feature to add compensation, and it should supply both voltage and power flow conditions. And here's an example for us. Here I took the rated kVA of the motor. I got the lock rotor multiplier from the NEMA code. I basically at 6.12, I calculate my kVA. I'm choosing a 0.15 power factor. Maybe I had it, or maybe I'm assuming what it is. I put it in here as a constant impedance load. This much kVA, this much power factor. I start the motor, and you can see that the voltage drops to 81%. And if I apply some compensation, it raises the voltage to 93.7. So that's a power flow simulation. It's one moment in time. So how about hybrid 1? It's going to blend a digitizing of the performance curves and the positive sequence network. So you should be digitizing the torque, the current, the power factor, and I think I listed torque there twice accidentally. So you don't need torque. Oh, excuse me. I'm sorry. That's the load torque. So to get that torque difference over versus speed, you have the motor torque over that you're going to digitize off, and then also the load torque. And that would look something like this. So here we have our performance curves. And unfortunately, this one doesn't have power factor. So just imagine that the power factor for the current is on here as well, and we're going to pull that in. So we're going to calculate an impedance from a speed. So obviously we're starting at 0 speed, but let's imagine we're somewhere in the middle of the start. So we're here, we're going to find us at this speed condition, we're going to digitize off this curve, the current magnitude and the power factor at the phase angle. We're going to calculate an impedance. We're going to stick that in our network model and we're going to solve it. And after we solve it, we take the voltage squared and we read off the torque, get the torque for the motor, feed it back, subtract off the load torque, and then do our inertial model with a time simulation. And this 1/s block just simulates integration is what it does. So that's our hybrid 1. All right. Hybrid 2 is very close to it. Oh, just in case you want a couple equations for yourself that might be useful, because you can notice I used H here, 2H for the inertia, and you don't have H. You can calculate it with this equation right here. H is a constant in kilowatt second per kVA, and these are typically in pound feet squared. There's a similar equation if you have the metric system. So hybrid 2 is very similar, except all it does is it uses a double cage circuit model instead of digitizing off of the torque speed curves. And a parameter derivation is necessary to get those parameters for the double cage model. And it looks something like this. Double cage circuit model. From this, you're going to calculate parallel. These are all in parallel. You calculate parallel, you put that in series, you get a Z at a given speed. Please note, this is slip, and this is the Laplace operator. So 2 different S's here, and I noted that here on the diagram. Going to take that impedance, stick it on the network model. We're going to solve the network with this impedance on it. Then we're going to take this voltage, feed it back so we can get the currents in each one of these legs so we can calculate torque. We take torque for the motor. We subtract off the load torque, which could either be digitized or from an equation. Like here, this is speed to some exponent. Very common, speed squared, speed cube model is very common. And in fact, this curve, I believe, is a squared curve right here. Goes through your inertia model, get your speed update. So as you simulate in time with the torque difference, and as it goes across the torque of the motor, it's going to speed up and eventually settle itself out. So these are hybrid 1 and hybrid 2. Couple things I'm going to note particular about these compared to this next model after I show this one. So the next detail is a full dynamic simulation. And if you're familiar with dynamic stability, that's what typically is done across the industry for utilities and simulating the whole grid infrastructure and its dynamic behavior. So for this type of model, we're going to need something a bit more sophisticated. And we want a full flux level detailed rotor model so that we can simulate the time constants in the rotor. But it will also use the positive sequence network and the inertial dynamics, similar to the previous one. So we're upping our detail. So parameter derivation is also necessary to get flux parameters, which are shown here. And there are some handy equations where you can flip between these two. So if you have the double cage parameters, you just go through some equations and you can generate these flux parameters, which I'm sure some of you have heard, X prime, X double prime, T prime, and T double prime 0. So the parameter derivation will mandate, similar to the previous parameter derivations, motor torque and motor current. And it looks something like this. And it's basically the same. The only difference is we have a substitution of a fully detailed flux model. And what you're going to find is that this model has the capability to feed back into the system. because it uses a Thevenin equivalent model. So we have a Thevenin voltage, a Thevenin impedance. This is hung on the bus. Basically, the model updates. The Thevenin voltage is right here. It's on a real imaginary axis. It has to be converted over to a Thevenin equivalent. It's hung on the model. We solve the model. The terminal voltage now feeds back. It affects a number of things in the model, and we need to calculate the terminal current. Also, the torque can be calculated from this model, and it's output here. So it's very similar to the last one, except we have a higher detailed model. And of particular interest, a couple quick notes. Because the dynamic model includes the Thevenin voltage source, it also includes the ability to supply fault current and voltage support. So you can see we transitioned now into a new level of detail. And this is critical when starting multiple motors on the same bus or when wanting to simulate motor fault current magnitude and decay. All the previous methods, the power flow, hybrid 1, hybrid 2, they don't include this detail. The transient model, which we're going to look at next, does. So for that model, flux level detailed rotor model, just like what we saw, but the stator is not a simple positive sequence. It's a full three-phase transient stator model, a full three-phase transient network model, the same inertial dynamics, pretty much the same. A parameter derivation is also necessary, and in particular, PSCAD, which we'll be looking at today, needs these parameters, which are the same parameters that we saw for the double cage network model. And again, a parameter derivation is necessary because we need to find those parameters from the motor performance curves. It includes full three-phase motor and network detail, and depending upon the upstream modeling and the detail that you put in there, there's a bit more data now. That data, positive, negative, zero sequence source of the transformer, possibly some overhead line geometry. If you don't know what the three-phase matrix, impedance matrix is, you can let the program calculate it for you. Transformer winding connections, grounding connections, the load torque equation or some form of a digitized curve we need to have to go with the motor model to load it down, and maybe some other models that we're going to look at. Soft starts, reduced voltage starters, these kind of things, compensation equipment. We're going to have to put our own models together for that. So full transient simulation is used to simulate the motor start over time, just like the previous ones. It updates the internal variable conditions, solves a simultaneous equation set, integrates all the models, and then it repeats over and over again to simulate your motor start. Note, inertial dynamics and rotor dynamics and all transient conditions in this simulation are performed together, which is different than when we look at the dynamic model, which has a separate static network model that then is impacted by the dynamic models. This is all one transient simulation. To get our answers, different from the previous ones, which will generate RMS results for us, we have to process the time waveforms and to extract the RMS, fundamental, and harmonic and transient information out of them. It would look like this. Now, I don't have the details for the inside of PSCAD or what it's doing. I showed you previous slides which showed you some internal details, and that's because I happen to have modeled some of these equipment, so I have some familiarity with that. But in PSCAD, you'd have your motor, your load torque impacting your motor, switching conditions, transformer model, source model. This is the most simple system, right, for us to look at. And by the way, works pretty good for almost all motor start simulations because it typically comes down to these critical factors. Now, there is a last method called finite element. It's on a different level, and we're not even going to really discuss that today. It requires extensive physical modeling of equipment. It can be used to see inside the rotor and the stator components and the iron into the windings to see heating, flux, current, voltage distribution. It's worth noting, but it won't be covered in detail here. So this is our spectrum of modeling detail and complexity. Power flow at the very bottom here, the simplest method, hybrid 1 and 2, which are very similar to each other. there's some space here between here and dynamics because this is a jump, because now you're getting voltage feedback effects. Also a jump going from here to full transient detail, and of course finite element is way off the chart in terms of physical detail. So a summary: we're going to ignore finite element. It's not practical for us. The power flow method is the simplest, requires the least data. The transient method has the greatest detail, requires the greatest amount of data and modeling. The dynamic method has real-time RMS response with the same network detail as a power flow model. The hybrid methods occupy some space between dynamics, full dynamic simulation, and the power flow method, and also use the same network detail as the power flow method. So what kind of tools are there available? Well, there's a bunch of them, and I'm sure you noticed these, or you know about these different tools that are available. The most critical important thing, though, is understanding your tool and what it's doing. It's essential behavior, and it's also essential to have confidence in its results, okay, that it's generating. So how do we get that confidence? Don't underestimate hand calculations and spreadsheets to verify your performance. I do this all the time. If I see a number that doesn't look right, I can do a quick 1/x calculation to see the per unit short starting current or whatever, to basically tell me, is this in the ballpark? Benchmark your tools, validate their performance. If you've got a measurement, boy, that's even better. Benchmark against a measurement of an actual piece of equipment. So have a sense or an expectation of the results before accepting them as correct. That's by repeat use of the tool and getting confident with it and building your confidence. So motor modeling in PSCAD. So we're going to jump into this, then we're going to look at some sag mitigation, and then we're going to look at our simulation results that we're getting performing and using this motor model in PSCAD. So for this webinar, this is our focus. The previous discussion was provided to basically show the various motor starting tools, what's available for us. The other simulations, and we're going to use them for comparison. I have a couple slides here to show you how they compare with each other. But why use PSCAD? Number one, reveal switching transient capacitive switching. That's important for us if we're supplying capacitive compensation. It includes the distortion effects of soft starts. It shows if capacitive compensation combined with a soft start is creating an unacceptable condition. It evaluates the application of harmonic filters and mitigating distortion from soft start applications. It can literally simulate real-time response of the equipment and the controller, which is also important. Is the controller going to perform the right actions during the start? It can see the transient voltage change for the on-off switching actions to optimize the motor condition sensing and logic settings for when we're going to close in and remove switches or those capacitor bank stages. And just for me, and I hope for you as well, it just feels better, right? It feels better knowing what we've got and we're not excluding detail. Why? Because that's often where potential issues hide, right? When you don't see it. So, a number of hurdles for PSCAD's analysis. Detailed data. Kind of have to have an idea of the start time. We have to have a tool to derive the parameters for us. A custom model, you have to build that inside PSCAD. Custom models for auto transformers, soft starts, VAR compensations. And the motor load starting conditions, we need to know, is it unloaded? Is it loaded? Are valves open? Are valves closed? The minimum motor performance data that I'd recommend that you need for PSCAD is torque versus speed curve, current versus speed curve, synchronous rating, horsepower, voltage, current, speed, power factor of the motor. I'm not going to list all of these. You can come back and see this again when you look the video again to see that these are the key things that are necessary. Here's an idea of performance data. Here's an example. What I like to do is cut the pieces out that are in other pages, and I like to paste them on this single image file that I have the performance data, so I have everything on one sheet. So you can see I've highlighted this in yellow for all the key parameters that go along with what I showed on the last slide. This is the tool that we would use And in this tool, you can see that what we want to do is overlay and match the actual torque speed and current speed curve, and then come up with these parameters here. A quick little thing to highlight. I like to estimate XM from the no load current if I can get it. Sometimes I don't get the no load current, but if I do, we can make an estimate of XM simply because under no load conditions, these branches are open because the slip is 0. So these are out of the picture. So all the current is flowing through here in the motor model. And these are very small. This is like 0.01, and this is like 0.01 per unit, and XM is like 2 to 3 per unit. So this is dominating. So if you have the no load current, you basically have an estimate of the magnetizing reactance, XM. Okay, calculate the inertia. Again, this is showing you how we take that equation. Just note in PSCAD, they want 2H instead of H. So you have to, J is equal to 2H, you just have to double it. Typical values range between 0.1 and 2 for H, for most motors, unless they're a special high inertia application, like a shredder or like a ball mill or something. You may find yourself getting inertial values all the way up to 9, 7 to 9. I've seen them that high. So here's some comparative results. So what we're comparing here is the full transient model in PSCAD, a dynamic model, the hybrid 2 model, and a power flow case. Hybrid 2 and hybrid 1, which will, by the way, will produce pretty much exactly the same result. So what do we see? Wow. Actually, things are really well correlated. Look at the power flow, the voltage dip, the current impact it's showing. It's right at the beginning of the starting condition, which is great. This is a hand calculation you can perform also. You can calculate this voltage dip and this current by hand and see how close you get. But this is a good indication as to whether your dynamic or your time simulation is realistic and in the ballpark. A couple interesting things. The transient model has a longer start time. It simulates an additional inrush that we're going to see is due to DC offset. It also has a power oscillation, which is also included within the dynamic simulation. And we can see that here. Sorry, went one too far. We can see that here in the power. This is the kilowatts and the kVAR for that same motor start. We can see that there's a significant power swing and it actually goes negative. So if there's anything critical that you want to see with a possible regeneration condition that's temporary, that could possibly trip off protection, you definitely want a dynamic or a transient model. Interestingly, the hybrid 2 is producing an unrealistic peak power condition, which means it's creating an unrealistic peak torque condition as well. The VARs are mapping very, very close for all of them. So we're getting some really excellent simulation matches. So this is benchmarking. I'm comparing 3 tools. I'm comparing, let's just go out of this just for a second. I'm comparing a PSCAD simulation and a hybrid 2 put onto the inside of a spreadsheet that I modeled myself. And we're getting really good answers. Now, I noticed something. I noticed that the starting time was a bit longer, which means I think that the PSCAD model isn't generating quite enough torque. So interesting, you can play around with the inertia. So if I increase it from 1.48 to 1.55, isn't that interesting? I can slide these two right on top of each other. Now I'm telling you, this is a freaking close match for 2 different simulation methods, completely different tools. This is the dynamic simulation in the Easy Power software versus the PSCAD modeling shown here. And they're laying right on top of each other. So I'm feeling pretty confident in the answers that I'm getting from this simulation. In summary, we can achieve excellent voltage sag results using the methods that we talked, and each one offers its specific flavor and what it's going to give you in terms of modeling detail. Power flow and hybrid methods exclude the ability to source current from other motors on the same bus. The dynamic and transient methods include greater and more realistic dynamic power response. The transient method includes that additional current inrush at the beginning, which is a higher current level, which could possibly trip protection, so that may be important to you. PSCAD transient simulations have a slightly longer start time, maybe from less torque, and so PSCAD simulations offer a slightly more conservative start time. Further, hybrid methods create a high, non-realistic power, breakdown power, which points to creating a much higher breakdown torque. So dynamic and transient simulations are preferable since they include greater and more accurate detail, and there's even more detail to see when we apply sag mitigation. So how are we doing on time? 10:36. We're making it. I hope everyone's doing fine. I hope this is not a death by PowerPoint presentation. I hope it's interesting for you. So before we look at the reactive compensation, let's look at the various ways that we as engineers perform sag mitigation on motors. These are the most common ways. Lower the system impedance. That's a big deal. It's hard to do, but that can help you. Reduce voltage starting, soft starting, wound rotor motors, which allow you to reduce starting current, Y delta motors, which is very similar to reduce voltage starting, the application of StatComs for VAR compensation, the application of adjustable speed drive to just basically eliminate all sag issues completely, and then the key one that we're looking at today with PSCAD, which is switch VAR compensation, which gives you a more economical approach to real-time VAR compensation. So how do we lower the system impedance to reduce the sag depth? Well, you got to go after the big stuff, replacing a transformer with a larger one or a lower impedance one. You can imagine infrastructure changes necessary for that. Upgrading a feeder with larger conductors, paralleling feeders. Not what utilities like to do, but it is there. Switching to an alternate feeder with a lower impedance. I've actually seen this done before, where a plant was put on a different feeder and routed from a different substation because it gave greater strength to the system. Relocating, literally picking up your whole plant, relocating it to a site with a stronger system. You can imagine how expensive that is. Paralleling transformers during starting. You're going to have, maybe you have two transformers, you have a double-ended substation, you can tie them together to double your short circuit strength. Now, since the system is linear, the reduction in sag depth is almost directly proportional to the impedance reduction. So you get a 1-for-1 here, but it does cost a lot of money, okay? This only reduces the sag depth, not the current draw. So let's list some caveats here. You can get rid of the sag depth, but you're not going to change the current draw from the motor. In most cases, all of these options are prohibitively expensive. Paralleling transformers could also create a breaker over duty condition. We can list even more caveats than this, but let's end with this one. We can have some things backfire on us. If we mitigate an in-plant voltage drop problem by upgrading our transformer, yes, the motor is going to start now, the voltage will be higher in the plant, but you're probably increasing the current draw on the grid side, which means the grid side, because you raise the voltage on the motor, it's going to draw more starting current. You could actually cause the grid side sag to worsen. So those are some of the caveats with lowering the system impedance. Now, how about reduced voltage starting? It reduces the sag depth by lowering motor current draw via voltage reduction. Delta Y, fixed transformer tap, caveats. Again, only employs voltage reduction. Equipment includes additional impedance. The transformer itself, poor starting power factor of the motor, it'll still impact the system, has current draw bump when it transfers to cross the line, lengthens the start time, no reactive compensation. And this is typically what it looks like. And you may have seen this in some of these simulator tools, especially on the coordination packages where they draw a motor starting curve and you put in reduced voltage starting. So yes, it raises the voltage from across the line, but then it has a bump at the end, and you can see the impact in both voltage and current from reduced voltage starting. Now, soft starts do the same thing by lowering the current by solid state methods and a voltage reduction on the output. It uses back-to-back thyristor switching. By using a delay on the thyristors, it reduces the voltage on the output. It incorporates predefined voltage ramping and current limits, but some caveats are it only employs voltage reduction. The poor starting power factor still comes right through the soft start, impacts the system. It lengthens the start time a lot, no reactive compensation, creates significant levels of distortion, and too low a current limit can cause motor stalls. And we've actually modeled this on the inside of PSCAD. Here's a soft start model. And this is the response we all typically see, right? We get great voltage is brought up in this case. Unfortunately, it's still pretty far below 90% at the plant bus, but it is helping from where we were for a cross the line start. But the one thing you typically don't see, and which is not talked about very much when people are looking at soft start applications, is how bad does it distort my system? So here I'm showing up to 15% voltage distortion in this case for this soft start, and you can see why, because it's drawing basically a 6-pulse bridge type current. Now, before you say, oh, that's your simulation, that could be really crazy, here's an actual measured soft start condition. It's pretty much the same on the voltage. This current looks a little bit different because the upstream impedance, this is a 480 volt motor. This is not a 4160 volt motor. So yeah, currents are phased a little bit, but we're still seeing the same distortion impact. Now, wound rotor motors. Let's not spend a lot of time on these. These are applications where you basically already have to have the wound rotor motor. This is not something you're probably going to use to fix a problem, but you're going to be aware of this. And I list that here, that if you have one of these, you should already be aware of the starting benefits, okay? And we can see that here on these curves here. You can see that as we increase resistance from R1 to R5, you can see the starting current at locked, for shorted rotor versus as you're increasing resistance. And also you increase torque. So we're going from black to the blue to the green to the purple. So that's one of the key reasons for wound rotor induction motor applications. In this case, I did a 5-step resistor application to show how I could step through different resistors on the rotor and reduce the starting current and improve the voltage. Y delta motor is going to be just like a reduced voltage start. So we don't need to go into much detail here. It does it by just having a Y winding and a delta winding. And when you apply the voltage first on the Y winding, it's like a reduced voltage across the windings of the motor. StatComs. StatComs reduce sag def by doing real-time VAR compensation. So they're reducing the motor current draw. They employ inverter-style VAR compensation. They can be fast, have 1 to 2 cycle response times. Inverter-style IGBT electronics corrects the poor power factor. So there's some real benefits here. Reduces the net motor starting current and reduces I2X losses, reduces the starting time. Some caveats. Depending on how the StatComs are filtered, or if they're filtered at all on the output, or not filtered, they can produce significant harmonic distortion. And interestingly, where are we applying these? Typically on the weakest part of our network, where just a little bit of distortion goes a long way. So since that's where these are applied, they typically will add some significant amount of distortion and switching noise on the system. They're expensive. And the equipment that's used for the starting application may or may not have the flexibility to perform other ongoing control actions. Finally, adjustable speed drives. And the one thing to just say here is, if you put this in, it's a lot of money to put it in, but you just eliminate, there is no sag because it'll just spin the motor up. It'll never go above rated current. The key caveats, again, like I said, is that it's really expensive. It produces significant levels of harmonic distortion. It's a really high cost. If this is only to help fix a sag issue, it's really high cost if that's all you're using it for, because once you start running the motor at 100% speed, it's less efficient with a drive in there, and if as compared to when it'd be across the line. So our key thing we want to talk about today. So with all that introduction, you see where we're going. You see the path I've been going along. Showed you the methods. Showed you the additional detail that we can see. And what I'd like to do is show 4 simulation cases for switched VAR compensation. And we're going to also consider some filters in these tools. So the reason why it works is it improves the power factor, reduces the starting current magnitude, raises the voltage, and reduces the motor starting time. So here's one of the devices that we can supply for you in 2 options, Power Megavar and the Synchro Megavar. The key difference between these two is that the Synchro Megavar applies point-on wave switching so that you can reduce your capacitor switching transient. And I'm going to show you an example of that. So for these 2 tools that we're going to put at this problem, or these 2 mitigation alternatives, again, the Synchro Megavar has transient-free point-on-wave switching, whereas both of them together offer ongoing load power factor improvement in addition to performing their starting action. So you can set it to maintain a desired power factor. They both are an efficient method of compensation. The capacitor filter application has far less losses than a StatCom's ongoing power factor correction. If you're going to use a StatCom to continue to do power factor correction over time, you have all the switching losses, the switching electronic losses. These offer harmonic filtering alternatives, so we can avoid creating harmonic resonance and filtering to reduce distortion caused by soft starts. They can be constructed from components in PSCAD. And this is the model that we put together for it. This is the induction motor model from PSCAD. We built the soft start model, the reduced voltage starter, and the Synchro Megavar, which is modeling both of these in one. We can switch between having point-on wave switching. We can turn it on or off. And then we have our upstream model. So we're going to be starting a 3,500 horsepower motor with a soft start and across the line, and with the Synchro Megavar system. The PSCAD modeling for the switched VAR compensation, here's the filter stages, and then we have a special point-on wave switch, or we can use the switch in PSCAD, which just does the general straight across the line switching without any point-on wave, or excuse me, asynchronous switching. So let's review these 4 simulations to show how the transient level detail gives you greater visibility into the application of the VAR compensation. In the first one, we're going to start the motor across the line, and we're going to include Power Megavar with asynchronous breaker closing, incorporate 3 capacitor bank stages, 3.5 megabars each, and the goal is to see voltage improvement at the PCC on the high side, where the utility is being impacted. Several runs were made to optimize this compensation, and here's what the simulation result looks like. So the across the line start is here in orange, and the blue is with the VAR compensation. And we can see that we're helping at the PCC. The voltage drop is to 85%. However, we're not getting it really above 95 here. We're staying pretty low here during the motor start. It's down around 93. This is a 7% voltage drop. And basically, this is not an acceptable condition. And by the way, we're applying 10 total megavars. Now, I don't know if you noticed in the model, this is a 5 MVA transformer. So that is a lot. That's actually overcompensation, and you have to be very careful with how you apply overcompensation. So this is where we stopped. Like I said here, the following simulation is a result where it seemed best to stop pursuing VAR compensation alone. So it looks like switch VAR compensation by itself kind of has its limits, and it can't really get us to the condition where we want to be. And also, let's take a look at the transient condition, because this is that additional detail. And we can see that, yes, it's okay. The switching you can see the stages switching on here, 1, 2, 3. And when they switch on, it's looking pretty good. We're not having any severe overshoot condition, and it damps out fairly quickly on the capacitor bank. So this was just a straight capacitor bank being applied. Now in simulation 2, we're going to use a soft start with no VAR compensation. And we're going to see how that works and see what it looks like. And again, the goal is to look at conditions at the PCC. So several runs were made again to get this optimized. And we're informed that the utility was unhappy with the present conditions and would allow only a 3% voltage sag. So this is an actual start, the soft start itself, and this matched an actual benchmark that we were supplied in terms of a measurement. So we are getting to, again, about a 7% voltage drop, and that was an unacceptable condition from the grid PCC side. You can see the 250% current limit, which was put in here and not allowed to go any higher because it would drop the voltage further. But if they put this current limit any lower, they'd stall the motor. So they were really stuck in a condition. They can't go any higher to basically keep from stalling. And so they're really stuck in a place there where they needed voltage correction, but they couldn't lower this any further without stalling the motor. Again, the thing that you don't see, like we showed before, is how severe the voltage distortion gets. And in this case, with this soft start application, it's a 15% voltage THD, impacting everything on the 4160 volt system. In simulation 3, with the soft start, we also now included reactive compensation to put them together. But in this case, first starting with just a capacitor bank. And in this case, we're going to apply it as quickly as we can, but we're going to notice that the soft start has a ramp at the beginning where you have to start switching on stages at that time. And again, we want to meet that 3% voltage sag. Unfortunately, because we're doing a full detailed simulation, we noticed that during the ramp up that there was a resonant and a problem with switching also the capacitor without using point on wave. And that condition is seen here. We can see a really bad voltage transient. I mean, this is like 1, 2, 2.5 per unit. This is something you don't want to have on your system. So this was without point on wave switching and without any form of harmonic filtering. If we put point on wave switching, we reduce the transient significantly. We don't have that high 2.5 per unit, but this is still an unacceptable peak voltage condition and a resonance that's occurring while it's going through this area of the ramp up on the start. So our last simulation, starting the motor with the soft start, with filtered stages at the 3.78 harmonic, 3 stages compensation, 4.8 megavar, point on wave closing is used. We're basically throwing everything at this and using the soft start with that 250% current limit. And what we see is an excellent starting condition. We can see that we're meeting the 3% voltage criteria here. We can see that we have minimal overshoot as we're taking stages off. We kind of dip a little bit here, but this is very short and very minimal. And we might be able to tighten this up a bit by switching the stages on a little faster. Here we can show that the current is reduced almost to rated current. This is in per unit on motor base, so this is like 100% rated current. During the ramp up, we can see that we just completely eliminated that bad transient condition. And we have nice, smooth response coming out of the soft start now. And if you were to plot voltage distortion over time, so the orange is across the line, the voltage is with the soft start being applied only by itself. You'll see that we're going up to that 15% voltage distortion level. When we apply the switch bar compensation with the filter application, we get it down to just 5.1%. which is what you really want. You don't want to expose your entire system to 15% voltage THD. Okay, in summary, transient simulations in PSCAD include critical detail for switch bar compensation, capacitor switching and ringing effects, transients, harmonic distortion, resonances, motor inrush, power swing effects, stall effects. Those are the kind of things that we want to make sure we're included in our simulation so we don't miss something. Supplies flexibility in modeling the electrical system and controls, naturally covers the full three-phase power system effects, supplies greater visibility into equipment behavior and system impact. That resonant, that ringing condition we saw, a lot of people would just apply the compensation without even running a simulation like that, and they wouldn't see it, and then it would bite them when they would try to start the equipment up. And finally, it allows for exceptional design analysis for client systems. So that's my presentation, and I got through it with 4 minutes to spare. So do we have any questions?
I've got a quick comment, Chris. Maybe you can speak to quickly the value of you mentioned benchmarking, but if there's a facility that's already up and running and experiencing a voltage seg due to a motor starting, whether it's on a soft start or reduced voltage auto transformer, or whatever it is, tell me what your recommendation is to capture that information and that data.
Yes, so you want to employ monitoring equipment and go out there, and I would do a stage test, starting the motor, or if you know when the motor is going to be started and come online, and you would want to capture the full RMS detail of the motor start. I don't think the transient will help you see interesting things that are going on. For instance, if you are employing a soft start, seeing that full waveform detail will show you how high the distortion really is going during the soft start. But at a minimum, the full RMS conditions, voltage, current, watts, VARs, cycle by cycle. I see there's another, did that help, by the way?
Yep.
Okay. It says
there
what
is a
type of
question in the
filters.
chat. Yeah.
Yes, what type of filters in the synchro megavar, notch or high pass? You can put whatever you want. But in this case, that on the simulation that I did, it was just a simple notch filter tuned at 3.78, which got it well below the fifth, and basically put it in a nice safe location for supplying augmentation, the VAR compensation that we need, while not exciting anything else on the network. Field measurements are priceless. Yes, they are. They're absolutely. And as I noted on the simulations that I showed you, we actually had a motor start capture that I benchmarked the model against to make sure I felt really comfortable that before I started my mitigating, I was matching the actual site condition. Any other questions? I hope that the presentation basically showed you the roadmap, or it showed you how to see what your tools offer and why, for instance, a company like Powerside would want to go after, some detailed transient simulation, why we think it's important and necessary. I hope that was the key thing to show you here, just the benefit from it and how it's aiding us to make sure we have a good application. How do you handle dynamic loads, i.e. the same motor may take 5 seconds one day to start and 10 seconds based on loading changes? Yes, what you could do is modify your load, your torque. The part of the model that supplies the load is the torque model, and you can change that depending on what condition you think that is under. How do you get that model? A couple ways. If you don't have it and it's not supplied by the vendor who's connected the load to the shaft, if you don't have the variations, like they don't give you 3 or 4 curves for what the loading could possibly be, then you have to kind of dream it up yourself. And taking a measurement, just like what we talked about, how important field measurements are, take a measurement of those variations and then perform modeling and changing your torque model until you line up with those starting conditions. That's what I would do. What is the control algorithm used? The one that was used in these simulations was looking at the motor VARs in terms of determining when to close the switches and then open them on the other end. You could use various types of controls, but for these simulations, I used motor VARs. I sensed them, a very simple control logic. All I did was say when the VARs went above a certain level, do it. And I think I could show that here. I go to PSCAD and I go to here and down here under the control logic. See, this is a nice thing about PSCAD is that you have logic, you have comparators, you have logic gates, you can do whatever you want for your control. So I just took in, I have a threshold here. Here's the cue of the motor coming in. I compare it against the threshold and I choose some logic here to basically turn on or turn off the switches. Yep, not that complicated, but you just have to think it through. Mm-hmm.
Fantastic, Chris. We are at time.
All right.
So I think we'll wrap it up. And of course, if anyone has any additional questions, please reach out to us at Powerside. Tom, I don't know if you have anything you want to add.
Nope, very comprehensive. Thank you very much, Chris. Look forward to getting the video out and available to the attendees. So thank you. It's very informative.
All right, everyone. Thank you for your time today. Hope you have a great rest of your week and weekend.